So the next topic that I'm going to discuss is electric field. Electric field. In order to understand what is electric field, I'm going to take an example of a magnet. Let's say that there is a small magnet placed, okay, in this manner. A small bar magnet. Magnet means it has two poles, north poles and south poles, right? Now, you take some small iron objects like iron nails, and place it closer to this magnet, okay? And place it closer to this magnet. Then, what will these iron nails experience? You have a bar magnet, okay? You have a bar magnet. Just forget about the poles of the magnet. You have a magnet. Now you bring some small iron objects, okay? And place it around this magnet, very close to the magnet. Then what will these iron objects experience? Force of attraction, alright? You take the same iron nails. You take the same iron nails and place it at a very larger distance. Then they are not going to experience any force of attraction. Right? Why? That means this iron or this magnet is creating something around it. Now, this magnet is creating something. Just say a field around it. Alright? This magnet is creating a field around it. And when you place the iron objects in this field, they experience a force of attraction. So that particular field, which is created by this magnet on a space around it, is known as magnetic field. Magnetic field. Are you getting me? So the same concept we'll use for the electric field here. Alright? Now, suppose just you take a point charge, point positive charge, and placed in free space. Alright? So you have a point positive charge, you have placed it in free space. Then, you take another charge, maybe like charge or unlike charge, and place it closer to this charge. Okay? You place it very close to this charge. Then what will happen? This charge, okay? Let me give the name, okay? Suppose you take a point positive charge and place it in free space. Now you take another charge, say Q naught. You take another charge, say Q naught. And this Q naught is known as your test charge. It's a positive test charge. I will call it as a positive test charge. Why test charge? Because the charge of this Q naught is vanishingly small. Vanishingly small. Very, 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 very small. Just like zero. Just like it has no charge. Is it okay? So you take this positive test charge and place it very close to this charge Q. Then what will this charge Q naught experience? What will this charge Q naught experience? Repulsive force. Alright? Now you take this same charge Q naught and place it at some infinite distance from Q. Then what will it experience? Nothing. That means, just like the magnet, this charge Q has also created a field around it, right? And when you bring any other charge inside this field, it experiences a force of attraction or repulsion. Electrostatic force means it can be repulsive or attractive, okay? That particular field created by this Q naught, where the electrostatic force of attraction or repulsion can be experienced by the other charges, is known as electric field. Is the concept clear? Yes. So the space surrounding a charge, okay, or a material body, in which the electrostatic force of attraction or repulsion can be felt by the other charges, is known as electric field. Alright? We can even calculate the strength of this electric field. In physics, strength we call it as intensity. How bright is the light? Intensity of light, right? Okay. So how strong is this field? Intensity of electric field. So intensity of electric field is defined as force experienced. So intensity of electric field is, or strength of electric field is defined as how much force is experienced, okay, when you place that test charge on that electric field created by any other charge. So force experienced per unit positive test charge. Actually, this test charge does not exist in real. It's an imaginary. See, yesterday we have studied, or in the last video, we have studied that the smallest charge that exists independently is, what is the smallest charge that exists independently? The charge of an electron. 1.6 into 10 to the power minus 19. Very, very small. But this test charge is smaller than this. Is it okay? This test charge would be very, 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 many times smaller than this. So whenever we write Q naught, we write limit Q naught tending to 0, as in the calculus. Limit Q naught tends to 0. It's this kind of charge does not exist in reality. It's just a theoretical creation to understand the concept. Are you getting me? Yes. So I'm going to write electric field as force experienced per unit positive test charge placed inside the field created by any other charge. And I'm going to write here limit Q naught tends to 0. So that's electric field. That's the strength of electric field. That's the intensity of electric field. Is it okay? Force experienced per unit positive test charge placed in the region, placed in the field created by any other charge. Is it all right? Yes. All right. Now what I'm going to do, I'm going to find out the expression of this electric field at any point. Okay? Expression for electric field. Expression, let me write. Expression of electric field at any point. I will not write as I'm giving you the notes, okay? I will not write as according to the notes. I will just explain the concept. You can make the notes, okay? Expression for electric field at a point due to a charge. Now what I'm going to do, suppose a point charge, a point positive charge Q is placed in free space. Alright? A point positive charge is placed at A. A point positive charge Q is placed at point A. Then this point charge Q will create a field on a region around it known as electric field. Now I want to determine the value of that electric field at any point P. At any point P. And let's say that this point P is at a distance r from the source charge. This charge Q is creating a field, right? Known as electric field, right? না তাই আমরা field to create করি আছে তো এটা আমরা তাই কি কব source charge কব and P is a point on that field and I want to find out what is the strength of the electric field at that point, and this point P is kept at a distance r from A. All right, now in order to do that, what do you have to do? I'm going to place vanishingly small positive charge known as test charge Q naught at point P. Why Q naught? Why I'm taking test charge Q naught and why not other any charge? Because Q naught is vanishingly small charge. It will not create any field on its own. Are you getting me? So we need Q naught here. Now, so the force, what kind of force will this Q naught experience? Repulsive force, because your source charge is positive. Q naught, even though it's vanishingly small, it's positive only. So it will experience a repulsive force. According to Coulomb, the force of repulsion between the two charges will be given by 1 by 4 pi epsilon naught into Q naught, product of the charges, upon square of the distance between them. Is it okay? Now, from the definition, electric field is defined as force experienced per discharge, right? How much force is experienced by the discharge when placed in the field of, in the region of electric field. It is your electric field, right? Yeah. So force, okay, F upon Q naught, can I write 1 by Q naught times F? No problem. So 1 by Q naught times F, your F is 1 by 4 pi epsilon naught into Q naught upon R square. Q naught can cancel out. So we have 1 by 4 pi epsilon naught into Q by R square. Or 1 by 4 pi epsilon naught is K. So KQ upon R square. So this is the expression for electric field at any point due to a source charge. In vector notation, if I want to write it in vector from C, let's say that R cap be a unit vector from A to B, means representing the direction of the force, right? In that case, your force will be, according to Coulomb's law, the force will become equal to 1 by 4 pi epsilon naught into Q naught upon R square with unit vector R, right? In that case, here we have found out only the magnitude of electric field. Now I'm finding the magnitude along with the direction. Then your electric field will be given by 1 by Q naught times F, right? So 1 by Q naught times 1 by 4 pi epsilon naught into Q naught by R square with unit vector R. Fine. So Q naught cancel. So your vector E is equal to 1 by 4 pi epsilon naught into Q R square upon R square into unit vector R. Now, we have learned the concept of vectors in class 11 physics. If A is any unit vector, if A cap is a unit vector, then unit vector A cap is given by vector A upon magnitude of A. So if R cap is a unit vector, then R cap can be written as, okay, let me write E here, 1 by 4 pi epsilon naught into Q upon R square. Unit vector R cap means vector R upon magnitude of R. So your electric field E will be 1 by 4 pi epsilon naught into Q upon R cubed with vector R. This is the expression for electric field in vector form. How is that? Okay, okay. So can you do it? I'm not writing according to the notes. I'm just trying to make you understand the concept. Okay. The resting depends on you. Alright? Yes. So I want you to derive the expression for electric field, okay, in finding the magnitude as well as the direction. Is it okay? Yes. This is a very vast topic of electric field, and now our main topic, okay, starts with the electric field.